Okay, we're continuing with the pre-algebra chapter in the algebra textbook. In this video, we're going to go through the third section, which is on rational exponents and radicals. Okay, so in section 1, we briefly touched on the idea of how we would represent if we wanted to. So, okay, we have an exponent term. Let's and a number to a positive integer power. You're multiplying that number by itself n times. Okay, but what if we wanted to look at sort of the reverse of this, the opposite of this, in the same way that division is the opposite of multiplication, or subtraction is the opposite of addition, and vice versa? Well, in that case, what we would be asking is, so this here, once you evaluate this result, okay, so you multiply b times itself n times, and you get a number, a. Okay, so to kind of go in the reverse of this, we would want to have some sort of operation where we input a, and we're asking the question, what number, when you take it to the n power, do you get a? So we would have this like operations box here. We'd put a into it, and what we would get out of it would be b. We have to specify, I guess, what the n is, right? What n are we talking about? What power are we talking about? And the question would be, what number, when you raise it to the power n, do you get a? And then we would be given b as the output. Okay, now what this is called is, what you're looking for are the roots of a, specifically the nth roots of a. So the square roots of a, the cube roots of a. You're looking for the roots of a number. That's what this is called. Okay, and the symbol we use to indicate roots of a number is the radical symbol. Okay, so if we wanted to find think about the nth roots of a, we would have this nth root radical symbol and put the a inside. Now, unfortunately, this gets a little bit complicated, whereas everything we've done up to this point with addition, subtraction, multiplication, and powers didn't have this complication. The complication is that, so if we think about the real number line, okay, when it came to adding or subtracting numbers, multiplying or dividing, or even taking numbers to a power, there was never an issue to where if you brought some numbers together to do like addition, subtraction, whatever, or you plugged a number into like a power, like took a power of a number, there was never an issue in the sense of that with all those operations, you always, the result was one and only one number. That was the result. If you really think about that, like, you could add, subtract, multiply, pick any numbers you want off the real number line, and even in the complex plane as well. This would work out for any complex number in the entire complex plane, where you could add, subtract, multiply, divide, or even take a power of even of a complex number, take a power, and the result is going to be one number, one and only one number, one unique number. Okay, but it doesn't work out this way when it comes to thinking about the roots of a number. There's an issue. Because if we think about it, if we asked the question, okay, if we took the number 25, okay, and we said, okay, what is the square root of 25? Which means we're asking what number, when you multiply it by itself, do you get positive 25? Well, there's two numbers. If you square 5, you get 25, and if you square minus 5, you get 25. Okay, now there's also the case of that if you have a negative number and you're asking for an even root of that number, what's the fourth root of this negative number, the square root, whatever, there's no answer to that. There's no numbers that when you take them to an even power, you get a negative number. But that's not so much of an issue. We've already come across that. So with division, you can't divide by 0, right? So we've come across an issue where like there's some scenario where there's no output, right? It's like undefined. Okay, so like the idea of asking for an even root of a negative number, we could think about, maybe we'll say it's undefined, like we did with dividing by 0, or what we're going to find is that we didn't have to keep it undefined. We were actually able to invent some new numbers that would allow us to take roots of find even roots of negative numbers. That's what the whole point of the complex numbers is. Okay, but the unique issue here is that we haven't seen before is that we're trying to define this operation here on a number, similar to how we define these operations, these exponent operations. But there's certain circumstances where there's like two potential outputs, and that's kind of a problem. We can't have, we couldn't be having division, addition, subtraction, division, multiplication, etc. Have certain scenarios where you get two outputs. Like you'd have like multiple, how would you simplify anything? If you're given an expression and you start to do the additions and stuff and there's something that comes up and there's two outputs, I mean, that's not ideal, okay? So what we do is we define this operation, this symbolic operation here, similar to like this exponent symbology here. We use this radical symbol, but we define it in such a way that if you're dealing with a radical symbol, you're calling that it's a principal root of a number. So which results in it's just going to be one specific root. Now, it doesn't mean that that all of the different roots don't exist. You can still think about, in general, what are all of the roots, the square roots of 25, and list those out. But for the sake of like dealing with equations and whatnot, and not having these ambiguous situations, we define the operation, the official root operation, as we call it a principal root of a number, and we use the radical symbol to indicate principal root. It's just one number in all cases. Okay, so in this section, we're going to start by talking about exactly what is the definition of a principal root, a radical here. How are you supposed to, every time you see a radical, how do you interpret a radical? Okay, now this is actually going to tie, though, directly into what we're also going to do in this section is, so we in the previous section, we defined what a number to any integer exponent meant, including negative integer exponents. But in this section, we're also going to come up with a definition for what would a number to a rational exponent mean. So a rational exponent is a ratio of integers. So like b to the 2/3. What would this mean? Or even b to the negative 3/4, or b to the 7/2. What does this mean? And we're gonna come up with a definition for this in a clever way, the same way we similar to how we did with the negative integers, and we're going to see that this is going to tie directly into radicals. And so that's why first we want to let's go ahead and talk about, make sure we understand exactly what a radical means. That it's the principal root of a number. Okay, so nth roots, or it says the definition of an nth root, but they're talking about here the principal nth root. When you see radical symbol, that means principal root, no matter what. It's a common misconception that, oh, you're only talking about a principal root if it's like an even index. Not at all. No, the radical symbol means it's the principal root. It's the whole idea that you're going to have this, it's a one root. When you say principal, you're talking about, you're saying forget all of the potential numbers that when you take them to the n power, you get this number. There's going to be one number that's coming out of this. One number. That's the whole purpose of the radical symbol. Okay? Now, one thing to note, though, before we really break this down here, is that, so, okay, but what about complex numbers? I guess like just before, just like we've been doing so far with addition, subtraction, multiplication, division, and powers, you know, even with x to the n, x to the minus n, whatever, we could input complex numbers. That was no problem. Complex numbers are, that includes all the real numbers, right? The entire complex plane includes real numbers. So we should be able to just input a complex number into a radical as well, right? Absolutely, 100%. But we will absolutely, at the end of trigonometry, we will learn how to take, so the entire complex plane, you can pick any number you want in the entire complex plane. It doesn't have to be on the real axis. You can find all of the nth roots of that number, and there's also, you can find its principal nth root. No problem. However, there's some confusion that actually comes up it can really trip you up. And so when it comes to radicals and complex numbers, so my recommendation is going to be that until you get to the complex analysis course, don't mix complex numbers with radicals. You don't want to be thinking about 3 plus 2i inside of the principal fourth root of 3 plus 2i. You can absolutely find the principal fourth root of 3 plus 2i. We'll learn how to do that in actually at the end of trigonometry as well. We'll learn how to do that. And you might think, well, so what's the big deal? Why can't we just write it out? I'll explain that more in trigonometry, and we're going to look into it in more depth in the complex analysis course. I would say don't mix in, at the moment, don't mix in radicals with complex numbers. It's just going to confuse you. Okay? Yes, you can still think about the idea. We're going to see how x to the 2/3, the meaning of this, we'll see this in a second, there is a radical associated with this. You can think about that. Yeah, once you go through the whole complex analysis course, you'll be able to, with no problem, think about this x as being a potential complex number, no problem. But for the moment, don't really go there too much. It's going to confuse you. And the reason why I'm saying this, I talk about this more at the end of the trigonometry course. But okay, for the moment, we're going to stick with real numbers. Right now, we're talking about roots of real numbers, okay? So, roots of real numbers. So, you can be asked, you can think about, if you don't say the word principal, if you just use the word root, okay, what is the whatever root of this number? So that when we say nth, you can think about, we're talking about nth is going to be a positive integer, really greater than 1. I mean, you could say the first root, I guess, but really any 2, 3, 4, 5, 6. What's the square root, the third root, fourth root, fifth root? It doesn't make sense to say what's the negative third root. No, right? Some positive integer really greater than 1. You could say the first root, I guess, but really greater than 1, 2 and above, right? So you could pick any number on the real number line and ask the question, what's the nth root of this number? But you're not saying principal. You're just saying what's the nth root. So when you do that, what you're asking in that case, since you didn't say principal, you're asking in general, what's the number or numbers that when you take them to the n power, you get this number? That's what you're asking. So if you said, what is the third root of minus 8? Okay, well, you're saying, what are all the numbers on the real number line that when I take them to the third power, I get minus 8? In that case, there's only one number. Minus 2 cubed is equal to minus 8. So you just list that one number. If you said, what's the fourth root of 16? Okay, well, what are all of the numbers? What is the number or numbers that when you take them to the fourth power, you get 16? Well, there's 2. 2 to the fourth is 16. Minus 2 to the fourth is 16. Okay, if you were asked, okay, what is the fourth root of minus 32? Okay, well, then in that case, you would say, well, there's no answer to that. There is no fourth root of minus 32. There's no real number. Yes, in complex numbers there is, but we'll get to that later. Thinking about real numbers, you would say there's no real number that when you take it to the fourth power, you get minus 32. Okay, and so what we can see is that the kind of the pattern here is, if you're dealing with an odd root, if n is an odd number, then what's going to happen is you can ask the question of any number, positive or negative, on the real number line, and it's going to have an odd number root, and there's going to be just one output. Like minus 2 cubed is minus 8, and then 2 cubed is 8. So again, if you have an odd n, an odd nth root, then it's really nice. You can pick any number on the real number line you want, okay, and ask what is its third root, its fifth root. It's gonna have an answer, and furthermore, there's gonna be just one and only one answer every time. Okay. Now, when it comes to an even root, issues come up because when you're dealing with an even root, first of all, you can't say an even root of a negative number. You can say 0, like 0 to the fourth power is 0, that's fine, but anything less than 0 is not going to have an answer. But then furthermore, even more than that, whenever you ask for an even root of a positive number, which has an answer, there's going to be two values. There's two answers. The positive and the negative are both going to be answers to the question. Okay? But again, when you're just asking what are the nth roots of this number, you don't say principal, then the implication is you're listing out all of the roots. Okay. It's only with when you're using the term principal nth root that you're specifying, okay, I want that specific number, that one number. Okay? So, and that's what the radical symbol is all about. So, what is the definition of a principal nth root of a number? Okay, so once again, n is going to be something greater than 1, some integer greater than 1. Okay, and we can start by, so, okay, a can be any real number, right? A could be any real number. We'll start there. Okay, but first of all, the idea is that the principal nth root of a is going to be one number b. One number. In all cases, this is going to be one number comes out of this. And then, but we will put the general meaning of a root with this one number such that b to the n power is equal to a. But this is more of the general meaning of root in general. We could have written this just talking about regular nth roots, not principal nth roots, right? But yeah, but it's going to be this one number b such that b to the n is going to be equal to a. Okay? Now, okay, we've said that n is an integer that's greater than 1. If n is odd, then we're done here. We're done. This is already done. You can input any number you want on the real number line, no problem, and you're going to get one output. And so it's perfect, right? Nothing more needs to be said. In the same way that when we define some real number to the n power, nothing more needed to be said. You could input any number you want on the real number line, any integer exponent, and you're going to get this one number as an output. Okay? However, there's the case we have to think about, what if n is even? Okay, so if n is even, so let's see. If n is even, we've already said n is an integer, greater than 1. If n is even, there's two specifications we have to put here. There's two issues. First of all, a is going to have to be greater than or equal to 0 if n is even. It could be 0, that's fine. But you can't input, you can, if you input a is less than 0, there's no answer to that, right? It's like dividing by 0. At least at the moment, it's like dividing by 0, but we'll be able to actually, with imaginary numbers, we'll be able to make it undefined. But at the moment, just talking about strictly real numbers, from the perspective of just looking at real numbers, a has to be greater than or equal to 0. But then we're not done. We have to, this is not enough because we have to have just one output. We have to make another restriction. The restriction is that b has to be greater than or equal to 0. That's going to be the restriction. It's going to be, in the case where n is even, there's two potential roots, a positive and a negative. We're going to return the positive. Okay? And so that is the meaning of a radical. A principal nth root. At least from the perspective of we're looking at just the real numbers, just considering the real numbers. Okay. Now, just to give you a preview, when we get to the complex numbers section in the next chapter, okay, we are going to expand this definition a little bit to incorporate imaginary numbers, just a little bit. And so we'll allow radicals to mix with complex numbers just a sliver. But we're not going to go any further than that until we get, not even to trigonometry, until we get to the complex analysis course. In trigonometry, we'll talk about what a principal nth root of a complex number is and what all the roots of a complex number are and how you find them. But we're not going to be mixing radicals, even in trigonometry. We're not going to be putting complex numbers into radical symbols. It's just going to be confusing. We'll talk about that in complex analysis. Okay, but before you get to complex analysis, we have one slight little mixture of radicals with complex numbers. Now, we're not, it's confusing because we're not really thinking about inputting complex numbers into radicals, even though real numbers are technically complex numbers. Okay, all we're doing is we're saying that for the one case, if you happen to have an even n radical that is 2. Not just any even radical, in it with n is 2. Then you can put a negative number underneath it if you're working on a problem where you're allowing for complex numbers. If you're not allowing for complex numbers at all, then you can't. But then you can do this, okay? And from there, you can simplify this by taking out an I, like that. And this is only the case where you can do this. You can only do this with a square root radical, okay? And so, but we'll talk about this more in chapter 1. But again, I just want to stress in this entire course, in this entire algebra textbook, this is as far as we're going to go when it comes to radicals and complex numbers. A negative number under a square root radical is as far as we're going to go. Okay. So now some notation here. The radical symbol, the principal nth root of a. You have the radical sign, the radical symbol with the n, the nth root. The n value is called the index, and what's inside the radical is called the radicand or the argument. Okay, so you've got here's the radical symbol, here's the radicand or the argument, and n is the index. And this is the principal nth root. Okay, so what would be the principal fifth root of 32? Well, okay, it's an odd root. There's only one number. When you take it to the fifth power, you get 32. That's going to be 2. Okay. What about the principal square root of 49 over 64? Okay, so what number, when you square it, do you get 49 over 64? And so there's going to be a positive and a negative, so we're going to return the positive here. Okay, well, we know with fractions, if you've got so a over b squared, we can write that as a squared over b squared. So we can think about then, okay, what number when you square it do you get 49? Well, that's going to be 7. What number when you square it do you get 64? Well, that's going to be 8. Okay, so in that sense, then we can see that. So 7/8 squared is going to be 49 over 64. But then, also the negative is going to be 49 over 64. But we're going to return the positive, so 7/8. Okay, the principal cube root of minus 0.008. So we have a minus inside of the radical. That's fine. It's an odd index. So, okay, 0.008, that's 8 over 1,000. Okay, let's see, 8 divided by 2 is 4. So 1 over 125. What we have is the principal cube root of minus 1 over 125. So, okay, similar idea to the previous problem. We can think about, so what number when you cube it do you get 1 or minus 1? It's going to be 1. Let's just put positive 1 for now. And then what number when you cube it do you get 125? That's going to be 5. Okay, but it's going to be the negative, though. Like this, if you take this to the third power, you get negative 1 over 125, which is 0.008, or minus 0.008. Okay. So negative 1/5. Okay, what about the principal fourth root of minus 1? Well, even index, but a negative number underneath. There's no real number when you take it to the fourth power that you get negative 1. So there's no answer here. Okay, now here, similar problem, but they just have the negative on the outside. Well, that's fine. There's no negative inside the radical. So what is the principal fourth root of 1? Okay, 1 to the fourth is equal to 1. Negative 1 to the fourth is equal to 1, but we return the positive. Okay, but now there's a minus sign out front, so there we go. Okay, now that we understand radicals, let's think about how we would define a number to a rational exponent, so a ratio of integers. What does some number to the integer n divided by the integer m mean? What would that mean? Okay, well, what we can do is we can think about how. So we're going to start with a to the 1 over n. Start there. Okay, what would this mean? Well, whatever the definition of this is going to be, we can think about it. We want to make it coincide with the properties of exponents that we talked about in the previous section. So these properties, right? We can think about we want this whatever this is defined to be in coordination with these properties. So in that sense, then we can think about what if we had 25 to the 1/2 power. Okay, so we have no idea what this means. Okay, well, if we would square this, okay, if we did that, then if this is going to coincide with the properties of exponents, then this would mean that we do this, right? Which is 25 to the 1st, which is 25. So what that would be saying is that 25 to the 1/2 power is a square root of 25. That's exactly what this is saying, right? This is 25 to the 1/2 is a number that when you square it, you get 25. But in general, a to the 1 over n is such that, so if you take this to the power n, you're going to get a. So what this indicates is that the in the rational exponent, the denominator is indicating like some sort of a root or a relation to a root. Okay, so but how can we represent since this a to the 1 over n is a root, an nth root of a, like 25 to the 1/2 is a square root of 25. Well, how do we represent a root of a number? Well, we can use the radical symbol, and we're going to use the radical symbol because we don't want to have this ambiguity of multiple answers, right? So we're going to use the radical to have these operations with these one outputs, these single outputs. Well, we can think about, well, maybe we could just say, since this is a square root of 25, so it's the principal square root of 25, right? This is a number that when you square it, you're going to get 25 for sure. That's based on the definition of a root. So there you go. It's perfect. We can say that a to the 1 over n is equal to the principal nth root of a. And there we go. That's the definition of a to the 1 over n. Okay? Now, but what about a to the m over n? Well, this isn't going to be a problem at all because we can just do a simple, just take a look at those properties again. We know that we can write this in two ways. We can write this as a to the m to the 1 over n, right, based on the properties of exponents, or we could do a to the 1 over n to the m. Okay, and so there you go. There's your definition. This would be like that, and then this would be and all of those have the same meaning. Okay, great. There we go. Now, what about some restrictions? What are some restrictions to this? Well, you can think about once we finish the complex analysis course, you'll be able to think. You can take any number with any radical you want, and you could figure out what it is in terms of and if you're considering all complex numbers, there will be no restrictions other than anything related to dividing by 0. Okay, but again, for the until you get to complex analysis, we're not mixing radicals with complex numbers, so it's just gonna create confusion. So what are the restrictions here if we're kind of thinking about we're only dealing with real numbers with the slight caveat that even or a square root of a negative number, you could take out an I with that slight caveat. What are the restrictions here? Okay, so it says, so if n is even, then a has to be greater than or equal to 0. Right? Because otherwise you're going to have a negative number underneath a radical. And that's it. That's the only restriction because we've got these are defined with radicals. So we're returning a single output anyway. So the only restriction is even even index or even denominator here, this has to be greater than 0. Like you might say, well, what if we had a positive number? What if we had something like this? Well, no, we can just it's the same properties. We do this. And now you've got, so the cube root of 2 squared, right? Now you might be saying, well, can't we do the same thing if we have a negative a with an even index? No. So if you had minus 2 to the 3/4, or minus 3/4, let's say, okay, so 1 over minus 2 to the 3/4, you got the same problem. You have a fourth root, principal root of a negative number. So it's only, you can't have, but also note that you could do this. You could say, so minus 16 to the 1/4, you can evaluate that because you don't have it in parentheses. That's different. Like this would be the minus, right, minus 2. So it has to, all of this has to be, raised to an even, with an even denominator. Okay, so let's look at these examples here. 25 to the 1/2 power. Well, we know that means the principal square root of 25, that's 5. Okay. What about 64 over 27 to the 1/3 power? We know that's this. Okay, well, we just kind of worked problems like this. We just want to figure out what number, when you cube it, do you get 64? That's going to be 4. What number when you cube it do you get 27? And so it's cubed, so it's only going to be the positive. 4/3 times 4/3 times 4/3 is 64 over 27. Okay. Now let's see. Minus 81 to the 1/4. Yeah, you have a negative number inside of an even root. There's no solution here. What about 32 to the 3/5? Okay, so yeah, here you just have to decide, are you going to put the power 3 inside the radical or outside? The way I look at it is, if I can clearly see, it's going to be easy to evaluate the radical as it's shown, then I go ahead and put the cube root, the cube on the outside, because the 5th root of 32 is 2. So done. But if it's not that clear right from the just first looking at it, then maybe you want to go ahead and once we would cube what's inside the radical, we'd see something that's clear of what the root is. Okay, now let's see, minus 27 to the 2/3. Okay, a negative number, but it's fine. It's an even index, or it's an odd index. So here I know what the cube root, or the principal cube root of minus 27 is going to be. So I'm going to do this. Minus 3 times minus 3 times minus 3 is going to be minus 27. And then, oh no, this is squared. And then minus 3 squared is 9. There we go. Okay. Now, next we simplify some variable expressions with rational exponents, and it notes here that it's really nice. The properties of the integer exponents, these properties, we can just extend straight to rational exponents, no problem. So we can apply all these properties with rational exponents, no problem. Okay, so with that then, so we've got this x to the 4/7 times x to the 2/7 over x to the 1/7. Okay, so to multiply these, the property of exponents is x to the m times x to the n, we just add m and n. So what is 4/7 plus 2/7? That's 6/7. Okay, now here x to the m divided by x to the n, it's x to the m minus n. What is 6/7 minus 1/7? That's 5/7. Okay, let's see. Here we've got 5c to the 3/4 over Okay, so we know like a over b to the m power, a over b to the m is equal to a to the m over b to the m. Okay, and then we also know that like a times b to the m is equal to a to the m, b to the m. So, all right, so we've got 5c to the 3/4, all of that squared. So we're going to have 5 squared times c to the 3/4 squared. So 2 times 3/4 is 3/2. And then d to the 1/2 squared is just going to be d. Okay, d to the 5/3 cubed is just going to be d to the 5th. And then we're going to have 2 cubed, and then c to the 1/2 cubed is c to the 3/2. Okay, so these two cancel out. This goes away, and we're left with, let's see, 25d to the 4th over 8. There we go. Okay, now 81 to the minus 3/4. So you might look at this negative with an even index and think, oh, well, we can't, there's a problem here. No, this can't be negative, the base here. So no, we can write this as 1 over 81 to the 3/4, which is so let's do the principal fourth root of 81 cubed. So let's see, 3 to the 4th is 81, 3 to the 4th, so 1 over 27. There we go. Okay, in the next video, we're going to talk about how to, so we just looked at simplifying expressions to where you start with the rational exponent expressions and you simplify from there. But what if we start with a radical expression? Right? And we want to simplify from here. That's what we're going to talk about in the next video.